Hello guys, we are SipSecure, the spiked drink detector. Before we get into more of the background material, I'd like to introduce the team. You have Greta Coiner, Sel Daltrich, Alex Gallegos, me, Vivian Newell, Jesse Shergill, Tara Stout, Caleb Sergai, and Caleb Zimmer. The problem we are addressing is drink spiking, which occurs when someone adds drugs to another person's beverage without their knowledge or consent. This is illegal in the United States, and the act of spiking a person's beverage alone is subject to a Class 4 felony. But that does not change the fact that according to a global drug study, this happens to 1 in 5 people on average. Our solution to drink spiking is our spiked drink detector device, SipSecure. It is a compact, discrete device that quickly tests beverages for these spiking drugs. If spiking drugs are present, a red LED indicator light will illuminate, notifying the user that their drink has been tampered with.
Given how common the crime is, many companies have been inspired to develop their own devices capable of detecting drink spiking. Of the many that have been developed, 3 prominent competitors have emerged: SwabTech, Drink Angel, and Nope. To allow for easy comparison between our proposed product and these competitors, we have created a table showcasing how these products perform in various competitive factors. These factors include the specific drugs the test can detect, the discrete or indiscrete nature of the test, the time required to conduct the test, the price per test, and whether the device is reusable. Examining the performance of SipSecure compared to the others, our device surpasses the competitors in discretion, detection time, price, and reusability. Unfortunately, as we are college students, we only have access to college-approved materials, including the drugs that we wish to use in manufacturing our device. Thus, we were unable to use ketamine for development and were forced to use a ketamine proxy, gabapentin. Overall, SipSecure offers something unique to consumers in the form of a discrete, fast, reusable, and cheap method for detecting drink spiking. Now moving on to the process description. After rewriting last year's SipSecure procedure, we've condensed the manufacturing from 8 days to 6, which can be simply explained through 5 steps. Step 1 is the creation and modification of silicon nanoparticles, pictured here. They are non-reactive, non-toxic, and chemically stable, allowing them to act as the backbone of our molecularly imprinted polymers, MIP, and non-imprinted polymers, NIP. Step 2 is generating the MIP and NIP utilizing the silicon nanoparticles, which act as our detective method. As NIPs are not exposed to gabapentin in their creation, they will not react with it, acting as the negative control for our device. The MIP, on the other hand, is molded for gabapentin and allows for the drug to complete the circuit. Step 3 is relatively simple, only modifying the carbon screen printed electrode via cyclic voltammetry so that it can readily accept the MIP and NIPs when applied. Step 4 is the transformation of the MIP and NIP into a membrane, which are then accurately drop cast onto the working electrodes. With the electrodes now complete, they are ready to be integrated with the rest of the circuit.
Our sensor works by comparing 2 signals that are received from the MIP and NIP electrodes. A sample of the drink that is to be tested is placed on both electrodes. We use the NIP as a reference to reject any noise or effects that are caused by the drink itself and not what we are looking for. Gabapentin travels through the holes in the MIP, causing an electrochemical response. This difference in response is then fed to an op-amp, which is amplified. Once this amplified signal passes a set point, an LED turns on, notifying the user of a spiked drink.
For our optimization work, we used a design of experiment approach to evaluate 2 response variables. The first was MIP-NIP sensitivity, since this determines whether the device can reliably detect harmful substances while minimizing false positives and false negatives. To test, we used a half-fractional factorial design to capture the most important effects while reducing the number of experiments. Because gabapentin is electrochemically active, it produces a measurable signal at the electrode. Sensitivity was evaluated by measuring the voltage difference between the MIP and the NIP electrode across a log scale range of gabapentin concentrations. The ideal condition gives both a strong signal and good linearity. Using the differential voltage allows the NIP to account for background activity and nonspecific interactions. The 3 CTQ variables for sensitivity were polymerization temperature, membrane volume, and template mass, since each directly affect the polymer structure and recognition site within the MIP. For the second response variable, we used the same DOE framework to optimize the user experience. This was important because even if the sensor works, the product will not be effective if the users cannot easily understand how to operate it. The 3 CTQ variables chosen here were device shape, device orientation, and user instructions. To evaluate the user experience, participants interacted with 4 prototype configurations and 2 versions of the user manual in focus groups. We measured metrics like comfort, clarity, ease of use, time to operate, along with the overall performance.
From our focus groups, we identified a few key preferences that shaped the final design. Users preferred a long, slim orientation and an oval shape, which felt more natural and ergonomic. For the instruction manual, they liked the organization of version 1, but the detail version 2, so we combined those to make a hybrid version. They also requested a few added features, including a battery indicator, a keyhole, and a straw or dropper kit. Overall, this feedback helped us refine the device to better align with user needs. The design process was highly iterative and developed week by week, driven by both manufacturing constraints and user feedback. We started with the Vivian, our baseline concept, long, slim, but very minimal in functionality. From there, the Sergei refined dimensions and the Zimmer introduced rounded edges as we began incorporating user input towards a more ergonomic fit. We then tested an alternative with the SideQuest, exploring a thicker design, but user feedback showed a clear preference against it, so we pivoted back. With the Greta, we began integrating key features like the cover and early cartridge concepts. The Alex improved the overall fit and functionality, making sure the components work together reliably. The Jessie required a redesign due to the circuit size changes, but also allowed us to refine the overall form. The Soul focused on validating the cover mechanism and cartridge integration. Finally, the Terra is our completed design. It includes a power switch, keyhole, and the fully integrated features, resulting in a polished, user-centered product ready for E-Days, ready for you to come see.
After optimizing the synthesis and sensor fabrication steps at the laboratory scale, the next challenge was translating that process into a manufacturable system. Here I'll briefly describe how the workflow was scaled from small batch lab procedures to an industrial process capable of producing about 19 million electrodes per year. The primary goal of the scale-up was replacing manual centrifugation steps with scalable unit operations while maintaining the same MIP and NIP sensing chemistry. In the lab, silicon nanoparticles were modified in round-bottom flasks with manual reagent additions. At scale, this was converted to a continuous mixing and reaction system where TMS-PMA is first rehydrolyzed in Mixer 1, then reacted with silicon nanoparticles in Reactor 1. Centrifugation was replaced with microfiltration, enabling continuous separation of modified nanoparticles before storage. For core shell MIP synthesis, the modified nanoparticles are suspended with MIP reactants in Mixer 2 and polymerized in Reactor 2. Instead of centrifugation washes, a filter dryer performs both solid-liquid separation and drying in a single unit operation. The same configuration is used in parallel for the NIP control polymer. The electrode fabrication stage also required significant changes. Rather than electrochemical deposition on individual electrodes, we implemented a roll-to-roll sheet process where electrodes are surface activated, printed with polyaniline ink, and dried on a conveyor dryer. Finally, the MIP and NIP membranes are prepared in mixers and printed directly onto the electrodes, replacing manual drop casting. The coated electrodes are then dried in vacuum ovens before distribution. Overall, the scale-up process replaces manual batch steps with continuous mixing, filtration, and automated printing, enabling consistent high-volume sensor manufacturing. Scaling the process to industrial production also introduces new safety risks, so several key feedback control loops were implemented to maintain stable and safe operation. First, reactor temperature control prevents unsafe temperature excursions during the silicon modification and polymerization reactions by adjusting cooling water flow in the reactor jacket. Second, reactor feed flow control maintains consistent residence time in the parallel reactors, preventing fluctuations in reactant concentration that could destabilize the reaction or affect polymer structure. Third, solid inventory control in storage tanks prevents overfilling or material shortages by monitoring tank weight and regulating solids discharge. Fourth, microfiltration pressure control protects the membrane separation by maintaining an appropriate pressure difference and preventing membrane damage or fouling. Finally, vacuum oven control ensures consistent solvent removal from the coated electrodes while preventing uneven drying or damage to polymer membranes. Together, these control loops help maintain safe operating conditions while ensuring a consistent product quality.
This radar graph summarizes our sustainability performance using the AKE's 7 sustainability indices. Each axis represents a different index. The light green line shows our initial performance, while the dark green line represents projected improvements after implementing design changes. Overall, the project demonstrates mid-level sustainability maturity. We perform the strongest in product stewardship and social responsibility, while environmental performance and value chain management remain the main areas for improvement. The graph also shows that most improvements come from design changes like increasing material circularity, improving supplier sustainability, and reducing environmental impact from the synthesis process. This highlights that sustainability is already integrated into the design, but still has clear paths for improvement. Looking at the 3 pillars of sustainability, environmental, economic, and social, we can break down how our system performs more simply. Environmentally, the reusable device is a major advantage because it reduces waste compared to single-use alternatives, and the low-power electronics limit energy use. However, disposable cartridges and solvent use in the synthesis process are still key challenges. Economically, the design is scalable and cost-effective. It uses injection molding and standard electronic components and relies on widely available materials and outsourced manufacturing, which supports large-scale production. Socially, the device provides direct value by improving user safety through drink spiking detection. It also uses low-voltage electronics and stable materials, reducing the risk to users. Overall, the system shows a balanced approach across all three pillars, with the biggest future improvements focused on environmental impact and supply chain sustainability.
SIP Secure requires about $2.5 million in capital investment and generates around $29 million in annual sales, with production costs near $23.8 million and about $5.5 million in yearly profit. The graph shown depicts cash flow over time with rapid profitability after the initial investment and stabilization, around $3 to $3.5 million per year. Overall, the project achieves over 200% return on investment with a payback period of less than half a year.
At the start of this project, we were given a total of $2,000. In the first semester, we spent a total of $700, primarily on chemicals. Second semester, we spent a total of $611 on mechanical parts, circuit boards, and any additional chemicals, with a total of $689 remaining.
In the fall, we had multiple setbacks for our schedule, the major one being caused by a lack of lab access. Despite this, we were able to create a relationship with Harasova and her lab. For the spring, we were able to rearrange our schedule to arrive at E-Days with a product we are proud of. In conclusion, we have had strong performances in all sectors of our project, with our lab team completing 4 rounds of MIP and IP development, focusing on improving the process in terms of time and output. Our business team has refined our product to align with customer feedback, and our mechanical team has worked in conjunction with them to produce the best possible user experience. With our product, users will be able to have a more secure night out.